I don't know how much familiarity you have with Zoom. Um, I've been working with the powers that be to try to get us an unlimited account so that we don't have to keep switching in and out here. Hopefully, we'll get some resolution by the end of the week or early next week, because this is tough. And if you're unfamiliar, basically how it works on my end is you get a you get a message, um, that at the 2 minute mark it says less than a minute to go. Doesn't count you down, doesn't say anything, just says less than a minute to go. So I've got a stopwatch here, and I thought I had another 15 seconds to wrap up. I it My camera shut off and I was done. So it kind of cut me in mid sentence there. Um,
The links that you gave helped though. Like it made it easier to.
yeah, well, that's so. Um, yeah, I think I'm gonna have to send a link actually because Brett hasn't found his way back into the room yet. Uh, Now, the good thing about those links is, if we have to keep doing it this way, um, it those links for session A, B, C, those will work regardless of the day. So you don't need to look for new announcements, new things from me every day. They'll work the same each day. So um, session A, that's our 9 o'clock link. Session B, that's our 9:40, 9:45 link. Session C, that's our 10:30 link. And so after this one, we'll take probably about a 10-minute break just to stretch out and stretch our brains a little bit. Um, all right, Brett, can you hear me?
Yes.
Okay. Brett, did you get the announcement last night that I sent about the Zoom links?
Yes, I clicked on the first link again and not the second one, so I was sitting there waiting on the wrong session.
Okay. Yeah, I was telling everybody else I'm trying to get us an unlimited account.
Okay.
Um, it's a little more expensive than what I want to pay out of my own pocket.
Yeah.
Um, I think they want like $150.
Oh, wow.
And that's just not something that it makes sense for me for a month. So I've been talking with the university to try to fix this, but those links that I sent work every day.
Okay.
And so if I get cut off, I'm trying to keep time here on my desk, but uh, I ended up being like 20 minutes short, or not 20 minutes, 20 seconds short, and so I got cut off in the middle of the last session there.
Okay.
So any questions about that example that we just did with the cup of coffee?
Mm-mm.
No. No.
Okay, so we'll start off the second session here by asking a question. If all of you could turn on your mics and just kind of talk out loud here some thoughts. Let's see if we can answer this question. Now that we've done a little bit of calculation work, the Fahrenheit and the Celsius scales are often referred to as relative scales, relative temperature scales. The Kelvin scale is often referred to as an absolute scale. do some brainstorming here, talk out a little bit. Are those two terms? What do they mean? And how do they relate to the idea that we talked about initially with the fact that temperature measures energy? So I'm going to kind of step back here. I'm going to mute myself for a minute or two here. I just want to hear you guys talk and try to come up with some answers yourselves there.
Okay. For the Kelvin scale, it is an absolute scale basically because it has an absolute zero. It has a point where there is no energy in a system. So that's where it bases its scale and goes from there.
And then the Fahrenheit and Celsius are relative because they have positive and negative temperatures.
Okay, I'm thinking that, I mean, I don't know if we're comparing the two, but like Fahrenheit and Celsius, that's like, I want to say the starting point, and Kelvin is more of the conversion to, or I could have it switched around.
The difference between Kelvin and Celsius and Fahrenheit is Kelvin has an absolute 0 point. So it starts at where there is no energy, and then it goes from there. That's what makes it an absolute scale.
Okay, I'm gonna put it down.
Yeah, that's why Fahrenheit and Celsius can have both negative and positive scale
Okay.
temperatures, whereas Kelvin cannot.
Okay.
Okay, some pretty good discussion in there. Now, I will correct one of the things that you said. The fact that we have positive and negative values doesn't necessarily mean that that's why it's relative. The terms relative here mean that we have defined values, and we're measuring values relative to those defined values. So what values are defined on the Fahrenheit and Celsius scales?
The boiling, the freezing with respect to water.
Exactly. So that's what makes them relative scales. And so because of those values, it necessitates that because there are values that are colder than the 0 point on the scale, then there have to be negative values. Whereas, Brett, I thought you put it really, really elegantly when you said that the absolute scale has an absolute 0 value. Well, technically speaking, the Celsius and Fahrenheit do as well, but they're negative values on both of those scales, and there's not a whole lot of sense that comes up with them. And so the difference, one of the things that let's go back to this. When it comes to energy, which of these two sets of scales is going to best define and measure energy?
Kelvin.
Kelvin.
Yeah, it's going to be the Kelvin scale, because in the Kelvin scale, since we have that 0 point defined and it represents a 0 point in energy, then everything else is relative to that. Everything else is defined as just being the next part in the linear trend. And so if I have something that's 50 degrees Kelvin and something else that's 100 degrees Kelvin, I know that the 100-degree object has twice as much energy as the 50-degree object. And if I have something that's 300 Kelvin and something that's 900 Kelvin, I know that the 900 Kelvin object has 3 times the energy of the 300 Kelvin object. That's the advantage of the absolute scale. Whereas on the Fahrenheit and Celsius scales, we can't do that. Take your cold day in Indiana. It's 5-10 degrees Fahrenheit. If If it's 5 degrees Fahrenheit today and 10 degrees Fahrenheit tomorrow, did the energy double in the system? No, not even close. It's still freaking cold. And so that's the disadvantage of those relative scales. They have their utility. They're a heck of a lot easier to measure because of those values and because of the defined nature of them, especially at the Celsius scale. But they lack that precision when it comes to measuring energy. Now, we're going to pivot here to talking about measurement. And in measurement, you saw this in the post-lecture last night, the terms that get thrown around often for measurement are accurate, precise, and exact. Those are the three primary terms. Now, there's the other one here where we can say that we have inexact measurements, or as we more precisely call them, measurements. Because most measurements, in fact, virtually every measurement that you take using any kind of instrument whatsoever has a level of uncertainty to it. But we talked about the idea of accuracy and precision, consistency. Now, when it comes to measurement, if it is something that we actually measure, then it is going to have a level of uncertainty to it. Because regardless of what instrument we use, there's going to be some level of estimation taken by that instrument, because we cannot know every single digit of that measurement precisely. Even if we have something electronic, there are tolerances and error bars associated with that. The only kinds of measurements that we can actually take that are exact are ones that involve counts. So if I'm counting pennies in a jar, I know exactly how many pennies there are if I count them out. There's not going to be any kind of estimation to that. Now, if I just look at a jar and go, oh, I think there are about 100 pennies in there, that's an estimate. I could be wrong. Good chance I will be, unless I'm just really lucky at guessing. But if I go through and I count it all out, and I find that there are 105 pennies in there, there's no uncertainty in that. There's no estimation in that. It is 105. And so when we get into calculations and when we get into doing measurements, the idea of uncertainty is a really important idea. It's something that is going to kind of drive what we do for a lot of the rest of the process here. So let's take a look at some of these things. First of all, let's make sure we understand the idea of exact versus measured. So 3 things here, 3 measurements. Which of these are exact measurements?
A golden nugget has
Yeah.
Okay. So Golden Gate Bridge, this is an exact measurement?
no, the golden nugget.
Oh, the Golden Nugget, that's an exact measurement?
Yeah.
I would say the steps.
Okay. So again, we have to go back to our idea of counting. The only kinds of measurements that are exact are those that we count. For the measurement of the gold nugget, did we count this number of grams?
No.
Well,
No.
oh, I thought it was saying like for the 893 steps, like you're taking them individually, not like the actual steps that are there. Never mind. Okay, yeah.
So if I start at the bottom of the Washington Monument and I decide to climb up the fire escape, I would count every single step that I took all the way up to the top. And there'd be no variability in this unless I miscounted. It wouldn't be 892.9 steps, because there's no such thing as 9/10 of a step. You either take a step or you don't. So this one, this one, letter I, is an exact measurement. Now, what about the width of the Golden Gate Bridge? Is that exact, or does it have some uncertainty?
It'll have uncertainty.
Yeah. Why, Brett?
Because it's measured, so it's only going to be as accurate as the tool that they're using.
Yeah. And what about the gold nugget?
That would also be. Oh, sorry. Go ahead.
No, I said what you said, uncertain.
Yeah.
Yeah. So anything that is measured is going to have a level of uncertainty to it. And so even though we've measured the mass of this golden nugget pretty precisely, I mean, 4 decimal places on a gram is a pretty precise measurement. That is as precise as our labs at VU get, to be perfectly honest. But that doesn't mean that this is an exact number. Even those kinds of balances with this level of precision have uncertainty associated with them. If I were to measure that same gold nugget on 5 different scales, what I would probably find is that there would be variability on that last digit there. And that's what we call an error tolerance. And every single measurable instrument, every single measured instrument has an error tolerance associated with it. Sometimes it's things like 1 or 2%. Sometimes it's things like, plus or minus 1 on the last decimal value. But every kind of measurement has those. It's an election year. It's 2020. Polling numbers guide you in the direction and say, okay, candidate A has a 4-point lead over candidate B. And you might look at that and go, 4 points, that's pretty close. Then they tell you the margin of error. Margin of error is 5%. Well, guess what? A 4-point lead with a 5% error is basically a 0-point lead. We don't know who's winning. We think it's this guy, but there's a 25% chance that the other guy's winning. So every kind of measurement, not just instrumentation, every kind of measurement has uncertainty associated with it. And the sooner we can kind of come to grips with that idea, the better things will be in terms of being able to use that constructively. And so, as I was saying kind of before, different instruments have different error tolerances with them. So this is kind of your typical laboratory balance. It's called a centigram balance. The reason it's called a centigram balance is because it leads to 2 decimal places, which would be the centigram place. This is an analytical balance, reads to 4 decimal places, but it has an error tolerance as well on that last significant digit, on that last recorded digit. And so the important thing to know is that regardless of type of measurement, we will always know that there will be one and only one uncertain digit in every single measurement that we take. There's only one uncertain digit. If I have more than one uncertain digit, then I have too much estimation going on. And if I have too much estimation going on, that's when we can get into errors. That's when we can get into mistakes. That's when we can make the wrong decisions on things. So we talked a little bit about this idea of precision and accuracy. This was in the post lecture last night. Precision is all about reproducibility of measured results. So if I take that gold nugget and I put it onto 5 different balances, do those 5 different balances give me the same value, give or take, that last decimal place? If they do, then we can call the balances precise. We can call the measurement of the mass of that gold nugget precise. If not, then we start looking at, okay, is there a problem with one of the balances, or You know, what can we do? Precision is often expressed by citing the range. So I take my highest measured value, I take my lowest measured value, and I express that range of values and say, okay, all of my measurements were between these two values here, whatever those two values are. The other way we can do it, and this is where we get the error tolerance idea, is we use the tolerance of the scale or of the instrument, and we just say, okay, here's the value, 2.8490 grams, and that's plus or minus 0.0001 grams. So that's precision. Accuracy is all about closeness of the measured value to the true value. Now, how do we know that our balances are accurate? Well, when you buy a balance, it usually comes with a small weight, and the weight is a known value. It's a standard, 25 grams, 100 grams, whatever the case is. And you put that on the balance, and you make sure that the balance reads whatever the mass is supposed to be. For thermometers, we usually use water. And so we take the thermometer, we put it in boiling water. We take the thermometer, we put it in freezing water, and we see what it measures the temperature as. Because those values are defined, it should be pretty easy to do that. And then we can calibrate any of those instruments by saying, okay, this balance was supposed to read this middle knob at 25 grams. It read it at 27 grams. Can I make an adjustment to the way that the balance works so that the 27 grams starts reading as 25 grams? Can I make an adjustment to my thermometer so that it reads the boiling point of water at 100 degrees instead of 101 degrees or 95 degrees or whatever the case is? So we've talked a little bit about significant figures. And actually, one of your post-lecture activities for tonight is a review of those significant figure rules and things. I'm going to give you a quick overview of that now, since we haven't seen it yet. And the quick overview is this. When we multiply and divide, the lowest number of sig figs in the calculation that's what gives us the total number in our answer. So when we multiply and divide things, we're going to look at, okay, there are 4 significant figures in that value. There are 3 significant figures in that value. There are 5 in that value. 3 was the fewest. And so that's the number of significant figures we're going to show in our answer. When we add and subtract, we're concerned about decimal place. So the way that we look at that is that the measurement with the leftmost estimated digit becomes the last sig fig in the answer. So in the case of the problem in front of us here, how many significant figures are in the measurement for nail 1?
That'd be
4.
4.
4. So when we're looking for significant figures, just keep in mind that all that we need to do is look at the number of digits that are there, with a few exceptions. So if the number is really, really small, we don't start actually counting the numbers until we get to a number that's not 0. For numbers that are really, really big, once we hit a trail of zeros at the end, we stop counting. But in this case, we had 4 sig figs in our first measurement. And how many in nail 2?
That would also be 4.
4, yeah.
I got a quick question on the sig figs.
Sure.
So let's say we're doing like a lengthy algebra problem. Let's say it contains multiplication and addition. Do you apply the sig fig rule after every step, or is it applied to the final answer only?
So good question. The way to handle those kinds of scenarios is this. After you do all of your adding and subtracting, do your rounding for those steps.
Okay.
So, let's say that we were doing this, we're adding all of these together.
Yeah.
That's when we would after we added them together, we would do a sig fig application.
Mm-hmm.
And then if I had to do multiplication and division after that, that value and all of the other ones get thrown into the multiplication and division that you would do afterward. Okay. So try to limit your rounding to as few times as possible. But basically, it rarely is a situation where you're going to do anything other than maybe an addition or subtraction followed by a division, followed by a multiplication. And so you just kind of handle them in turn. You do the addition step or the subtraction step because they're done the same way, and then you do the next step.
Okay.
And you end up rounding twice, once after the additions and then at the end. Okay, so nail 3 has 6 significant figures, but since we're adding, we're not actually concerned with the number of sig figs. We're concerned with decimal place. And so what's really important here is we want to know where that last significant digit is. And for the first two, it's in the second decimal place. In the last one here, it's in the 4th decimal place. So when I look at my values here, adding and subtracting, the measurement with the leftmost estimated digit is the last sig fig in the answer. So the leftmost significant digit would be the second decimal place, not the 4th. So after I add all of these together, I'm going to need to round it to 2 decimal places to account for that. So I do my addition. $13.47 plus 13.43 plus 13.4653, and the answer that I get for the total mass, according to my calculator, is 40.3653 grams. But again, the problem here is that not all of these digits are significant. And I need to round to just one significant figure. So I've already highlighted that the second decimal place and the fourth decimal place are estimated digits. I can only have one estimated digit. So I'm going to choose the one that is the leftmost here. And so the actual mass that I'm going to record is 40.37 grams. Why 40.37? Well, that second decimal place is the last significant digit. So I need to round at that digit. Since the number that is directly to the right of it is 5 or greater, I'm going to round that 6 up to a 7. If it was 4 or below, I would leave it as a 6. But since it's 5 or greater, it gets rounded up. All right, any questions?
No.
All right, so let's look at the kind of the last part of this particular chapter is the idea of conversion factors. And so in conversion factors, we're taking all of these concepts and we're kind of smashing them all together. So our concepts of measurement, our concepts of units, our concepts of conversions, our concepts of calculations and significant figures, all of them get put together when we do conversion factors. Now, the way that conversion factors work is essentially conversion factors allow us to convert from one unit to another by taking equivalent values and turning them into fractions that we can use to cancel out unwanted units. So one of the things I like to say in this kind of regard is that when it comes to conversion factors, any two units that we can link together with an equal sign are perfectly fine for a conversion factor. Any two things that we can link together with an equal sign can be turned into a conversion factor. All I need to do is take one part of that equal sign and turn it into the numerator, and one part of that equality and turn it into the denominator. And which way I go with it depends on what I need to convert. Because ultimately, what I need is that the units that I'm trying to cancel need to be on the opposite end of the fraction of how it's designed in the conversion factor here. So if I have kilometers in my numerator of the unit that I'm trying to convert, I want to make sure that kilometers is in the denominator of the conversion factor. If kilometers was in the denominator, I would want to make sure that it's in the numerator of the conversion factor so it cancels out. And so that's all that this is really getting after. This is all that it's really wanting us to do here as far as this is concerned. So this is a listing of all the common conversion factors between the customary system, that is the system that the United States uses, and the metric system, which is pretty much what everybody else uses. Now, I'm not anticipating and I'm not expecting you to memorize this list. In fact, I'm strongly discouraging you from doing so, because this factor table will be included. If you go on the Blackboard and look at the prep areas, you'll see a equation list in the reference materials there. That equation list is something that you're given for every quiz and every test. And on that equation list is this particular conversion table. So you don't need to know that there are 2.205 pounds in every kilogram, or that a mile is 1.609 kilometers. You can look those things up on the table. Now, as I mentioned earlier, the metric prefixes you are responsible for knowing. So you do want to spend some time studying up on that. But as far as these are concerned, don't worry about them. You'll be much better off just knowing how to use them. And so I'm actually going to stop right here. And does anybody have any questions?
I do not.
No.
Okay, so it is 10:17 right now. Why don't we take a break? We'll come back around 10:30 or so, and we'll just do a series of practice problems with unit conversions, and that'll kind of close out chapter 1 for us.
Okay.
Okay.
Okay,
Okay.
so get up, move around, take a brain break, and we'll come back around 10:30 or so.
Okay, sounds good.
All right, I'll see you then.
Yep, see.